Recording has started. Cool. So I'm just gonna record this. There is someone on the call, and I know there's some people that aren't able to join us today, so it'll be there for reference. So yeah, thank you guys for all coming out to KiCad workshop. Just as a rough like estimate, who has prior experience with KiCad? Shaky. Cool. Okay. So yeah, this is going to be very good, like basic skills going into KiCad. It'll go over some fundamentals, but it's not going to cover everything. We could be here for hours. But as a caveat to that, I've included just like additional resources at the very end that I think are pretty helpful going forward into the projects that we're undertaking this year. So to begin with, I'm going to preference this as saying I am not a hardware engineer. Yes, I've used KiCad in the past, but I am not absolutely fantastic and proficient in this. However, I do know some good tips and tricks to use. So today's agenda, 5 W's of KiCad, who, what, where, what, when, and I threw in how. We're just going to briefly touch on like what PCBs are, what they're made out of, just kind of like some fundamentals that way. Then go into what goes on in building out a KiCad project, kind of the workflow and the steps required in order to build a PCB. And then we're going to try our hands at making one ourselves and basically make a little stoplight. So some LEDs, resistors, connector mounting bolts, all that good stuff. And then, as I mentioned, there's additional resources at the end that talk a lot more on what other features you can do with KiCad. And of course, like this is like super informal, super casual. So like this can be very much a discussion. If you guys want to ask a question, please just feel free to interrupt me and go. So we're just gonna start with some like background knowledge, and then the actual like hands-on is gonna come in just a bit after. So starting with the 5 W's, the first W, what is KiCad? So KiCad is a free software suite for electronic design automation. It's used to facilitate the design as well as the simulation of electronic hardware. And it basically features a whole plethora of different programs that are used for schematics, PCB layout, and simulations as well. And so what those look like when you download KiCad are all of these. So these are all the different programs that come packaged in KiCad. For our purposes today, I really just want to point out just a few. So this schematic editor is called VE Schema, and it's what you put all your circuit symbols and what you would see in like a circuits class or any circuit diagram. When we make our own, we'll start in the schematic editor and put all our components in. The symbol editor is if the symbol or schematic symbol you want isn't actually in the default library, we can make our own. If there's a new chip that isn't in the library, or you've made your own part, you can make your own and include it there. Next is the PCB editor, or PCB new. This is where you actually get to do the routing and the layout and the footprints of all your components. And then, of course, there's a footprint editor as well. So every component, and we'll talk about this a little bit later on, but every component has a symbol. Every component then has a footprint, and then every component has like a BOM item associated with it. So your symbol is just a little squiggly line you would see on a circuit diagram. Your footprint is the actual like square area that it would take up on the PCB. And then the bottom item is the actual like physical chip, physical resistor, or physical component that would go on the PCB. And then all of these other tools are just used to basically make your PCB a bit better. So your image converter, you can actually convert images into PCB footprints or silk screens. So if you want to do a logo, you can take your own cool, fun logo, convert it using an image converter, and then have that silk screened onto your PCB. Or if you have some fancy footprint that you want to do, let's say, for example, you're trying to build out a PCB for a quadcopter, and you have the body of the quadcopter and you have the arms going out, you can actually cut out your PCB in that exact footprint using like the image converter. As well, there's calculator tools that are used for what's called impedance matching, and we can talk about that a bit later. But just so you know, that KiCad itself, it's a suite of different programs that are all used in order to build a PCB. Any questions on that? Cool. So where is KiCad? Here's the download link. Does everyone have KiCad at least downloaded? Does everyone have version 6 downloaded, the newest one? Yep. Perfect. Oh, okay, sweet. Cool. So we're all good then. So moving on to why we're using KiCad. Teams used it before. We've built our own solar panel PCBs, which you may have seen on our old satellite. And then as well, we've also developed an OBC board. And so this is the lovely work that occurred last year. And you can see all of this fun stuff going on. So these are our different connectors. We have mounting holes here, and all the red and blue lines are all the different traces that connect all of the components together. So I know this looks like a lot, but this is kind of like the final product that takes a few months to develop. We're going to start some a lot more simple than that. And then moving on to why we're doing this workshop and what we're going on with this year. Pretty much every single subsystem is building out their own board. So for OBC, we have daughter board. Is there a name for that yet? Just daughter board. Okay, cool. COM, there's RF board, antenna deployment board. ADCS has actually 3 different boards, and then EPS has 2. So pretty much every single subsystem requires a board. And the beauty of being on satellite is we make everything on rover. They buy a lot of pre-built things, so they don't get this experience. So that's why we're one of the reasons why we're better than them. Again, there are a lot of PCB tools out there. So there's it's the one that starts with an A. Altium. Altium is a really common one used in industry. However, it's there is a paywall for it, and there's also a program called Eagle, and it's the same kind of thing. It has a lot of features, but you do have to pay for it. KiCad is open source. It is pretty much made for hobby developers, but it does have a lot of amazing features, and it's all for free. I have not found any limitations with KiCad, and all our past projects have been used with KiCad. So might as well continue on the trend and use it for this year as well. So like I said, we have had past projects that are all on our GitHub. It's as easy as going into GitHub, downloading the PCB repository, and then just opening up the project file in KiCad. So then you can see all the work that has been done in the past. As well, I've also started some templates. So if you're starting a new project, there is a PC 104 template that's available. So it's just the standard board that will fit in a satellite that comes blank. However, if you're thinking about starting a new project and want to contribute to the team, maybe start thinking about how you can first build out a template for that project, and then do your custom work on top of that, so that you can share the template with all the remaining members. So looking at what goes on in KiCad projects, these are pretty much all the files associated with it. Because you have a lot of programs, you end up generating a lot of files. And I know it can be a little intimidating at first, especially with all these .KiCad, .sch, .net, .libs. Every single one does have a purpose, so don't be too overwhelmed. They are all end with .KiCad now. This is new in version 6. In version 5, they usually just they have the KiCad removed, and it would just be .sch, .pro. With KiCad version 6, it is backwards compatible, so you can use both the .pro and the .KiCad_pro, and they're the exact same thing. So just going them one by one, the .KiCad Pro, that's your project file. And so it includes all the information about your project parameters and the, I guess, like configuration of your environment for the entire project. Then going on to the SCH, which replaces the old version of the .sch. This is the actual schematic file. So this is where you see all your circuit diagrams and all the symbolic symbols in the schematic. The .KiCad PCB is pretty self-explanatory. This is your PCB layout file. And what KiCad does is periodically create backups of your PCB files. So if you ever see a -save.KiCad, this is just a backup file as well. Then the .KiCad PRL, this is your project local file. So these are just some of the custom parameters that aren't included in your profile. And it's just used for different user interface setups if you're across Mac, if you're across Windows, or if you have custom settings for your UI. Then there's the .KiCad symbol, or SYM, and this is your schematic symbol library. So as we said before, every component has an associated symbol, footprint, and BOM item, and all the symbols for an item will have an associated .KiCad SYM. And then on the previous screen, we saw that there was a .lib file, .ecm. These are all now replaced with the .KiCad. So actually in this project, there's parts of version 5 and parts of version 6. But that just shows that it is backwards compatible, and you can use files from both. When you download a project, so I should say this, and you want to like open the project, like I said, what you're opening is the .pro, and then that will open up KiCad, and you can see all the other files in the eSchema or PCB new software. Moving on, so you have a schematic symbol library with the .KiCad sim, and then KiCad does something a bit weird. They have this .pretty file, which is your footprint library. I don't know why they just didn't call it .footprint, but every component will have a .pretty file associated with it, specifying the footprint. And most of these documents are actually just text documents. So you can actually open up these in a text editor and see exactly what's going on. It's usually like an XML format, And for example, the footprint will just have like a bunch of XY coordinates and like vector parameters that show like it has a line here that starts here and ends here, another line here that starts here and ends here, just specifying what the footprint actually looks like. And so with the .pretty also comes with the .KiCad mod. And so these two work together. One has the description, and then one's the actual library folder. Or sorry, the KiCad mod is file that exists in the .pretty. And then lastly, the .net. So this is your netlist file. And what a netlist is, it describes all the connection points between the different components. So like as a super simple example, what you could have is like a resistor, an LED that gets connected to ground. So then this is one component, this is another component, and then what a net is the connection between each component. So then this will be a net. Make sense? Cool. So yeah, biggest takeaways from this. Each file has its own purpose. There's a file for the project itself. There's a file for the schematic. There's a file for the PCB. There's a file for the footprint of each component. And then there's just some accompanying files that go into the project itself with the user interface and stuff like that. So that's kind of KiCad at a really, really high level. KiCad is a software suite of a bunch of different programs, all used to make PCBs. And the way they do that is they have multiple programs that use multiple files. Each file is associated with a component and the PCB itself. And so moving on to the next step, we're going to go into PCB review for a first look, if that's all right. And so what a PCB is, it stands for printed circuit board. And the way they're made is instead of having components on a breadboard or just loosely connected together, what they have is on a board, you're able to attach a component on top or through the board, and then have their connection points routed on the surface or connected through different layers of a PCB. And so a PCB comes in different layers. As you can see here, there is a top layer that has different traces. And what a trace is, connects two different components together, or you can think of it as just the like the wire that you would use in a breadboard, or a wire that connects two adjacent components. It then has called a dielectric layer, and so this just separates the signals and the voltages and currents happening on one layer from the voltages and signals happening on this layer, so they don't really interfere with one another. So you have traces on one layer, a separation layer, another layer that you can have traces and connections, another separation layer called a core, and then it just repeats again. So this is a 4-layer board. You can actually have 2, 4, or 6 layers. Today we'll just be building a 2-layer board, and so you'll have a top layer, a core layer for your separation, and then just a bottom layer. So all of this would be removed in a 2-layer board. So we have layers, we have traces which connect all your components together. And then you can also see here, these are called vias. And what vias do is they allow you to jump between the different layers. So if you have adjacent traces, they of course can't intersect with one another. Then, so if they do, they might interfere and they're going to be used for different purposes. So obviously they can't connect. So what you can do instead is, let's say we want to have this trace go continue on over here. What we can do with a via is continue this trace, go down a layer, make it move across the second layer, and then have it come back up and continue on. So vias allow you to transition between different layers in order to reach down to a ground line, power line, or basically hop over a different trace. And then moving on to different components that you can use on top of a PCB. There's two different styles. There's what's called through-hole and then surface mount. For surface mount, it's pretty self-explanatory. They are just located right on top of the PCB, and they are soldered onto what are called pads. So pads are just exposed copper that connects onto one of the traces. Now, with through-hole components, you basically have a through-hole that goes all the way through the PCB, and your component, its leaves coming off of the component go all the way through the holes, and you have the complete connection through that hole. So you can think of this, let's say this is your power, this is your ground. What you would do is have a resistor that would go through here and get connected on either side, going to using a through-hole component. Now, I know that was just a lot of information and not a review for some people. Does anyone have any questions about through holes, surface mount, what vias are, what traces are? Cool. So we know some background info about KiCad. We now know some background info on PCBs. So how do we put that together into a KiCad project? So as I mentioned before, every component has a schematic symbol, which as I draw on the board, this is what you would see in your schematic diagram as an associated footprint. So this is what is actually being placed or designed for on the PCB. And then this is your actual item itself that is associated with the two. So knowing that, the general structure of a KiCad project is you first start with your schematics. So you identify all your parts and all the connections between each one of the parts. After that, you assign the footprint to each one of the parts. So for example, you could have in your schematic a USB receptacle. However, USBs come in many form factors and many different packages. So that's why you have this KiCad, and KiCad doesn't know which USB receptacle you want. So you have to tell it what footprint to use, which USB receptacle to use. So then once you have your schematic and all your connections made and all your footprints assigned to each one of the components, then you go into the layout. And it's actually the physical layout of all your components and their placement on the board. After you have a general idea of where you want all your connectors and your components to be, then you go into routing, which is connecting all your components with the traces and the vias that we just mentioned before. Now, this layout and routing stage, it goes back and forth, and sometimes you even have to go back to your schematic and make changes to that to make sure that your connector pinouts are compatible. You might have to rotate a few things. You might have to swap pin 1 and pin 2 just to make the layout and routing a bit easier. And so this step is a bit back and forth, because you always want to minimize the size of your PCB to make it cheaper, but there are requirements for your routing about your trace widths, your separation, and because you only have so many layers, you can't always go into the most direct path. Sometimes you have to loop around. That makes the size of your board a bit bigger. So after you're happy with your layout routing, you go into rendering, which you can actually see the physical PCB and then produce what are called Gerber files. And what Gerber files are the files you provide to PCB manufacturer, in which they take onto their like CNC machines and their milling machines and actually produce each one of the different layers. And so after you've reviewed and rendered out your Gerber files, then you filled out your BOM and do all your purchasing. So for today, we're just going to do schematic, footprint, layout, routing, and rendering. We're not actually going to go for the full BOM and purchasing. If you guys want to, I encourage it. But that's just a lot of additional steps that I don't think we have time for today. And so what we're going to cover in the workshop is the components, symbols, and footprints. We're going to talk about traces, as well as something called copper pores. We're going to talk about and use vias. We're going to show how to use the different board layers. We're going to use silkscreen and include things called edge cuts, which is just the outer border of your PCB. Do I have? Yeah, and these are other things that we should consider as well. There's things called differential signals, and then there's a whole study on via sizes and trace sizes that are the most optimal for your design. We're not really going to look at that too much, but just know that there's a lot of consideration that goes into all these dimensions. But for now, I've just given you some rough estimates that we can use for our project today. So what we're going to do today is build this little traffic light. So as you can see, it has 3 LEDs, 3 resistors, a connector, and it just has some nice silk screen to identify all the different components. What we can do is either, if people are feeling confident, they can go onto this YouTube link themselves and try to follow along there, or I'm just going to do it on my computer and we can all kind of do it together. Cool. So I'll start that now. Oh, this is going to be tricky. Nice. Okay, so yeah, as soon as you open up KiCad, which I encourage everyone to do now, you can see all the different programs that are associated with it right on the main page. I was working on something else, but for now, we'll go into File, New Project. and then call it something appropriate. Cool. So every time you generate a new project, KiCad will do for you is create your .KiCad PCB, your .KiCad schematic files. And so going with the general steps for a KiCad project, we'll start with working on the schematic. And you're brought to this blank page here. So with this blank canvas, hard to see. There you go. Turn on the blank. Yeah, cool. So there's two main menu bars. One up top has a lot to do with just viewing and controlling different settings. The one on your right-hand side is more so with actually building out your schematic itself. So on the right-hand side, this little triangle symbol is where all your symbols are located. Underneath that are more symbols, but just specific to power. So it includes both power and ground connections. Underneath that is adding a wire or a connection point between multiple components. Underneath that is something called a bus. And so that's just a specific wire that is designated for multiple entry points and multiple components to attach onto the bus. It's basically the same thing as adding a wire, but it's just allowing KiCad to know what you're using it for to help you with the routing later on. After that, it's just more bus support. After that, it's something called a no connection. So, for example, if you have a USB connection or a connector, USB comes with power, ground, and signal lines. What's really common is you can just use a USB connector for power and not use the signal lines. And so what you would do is, and just make KiCad happy, is add a no connection flag onto the signal lines that you're not using. As KiCad does a lot of like electrical rules checks. And so if you have these, it'll basically like settle down any errors that you would see. And then after that is called a net label. Yeah, Joe. Oh, okay. I wonder if. Oh, yeah. That's not right at all. Okay, I think that might be better. I'll do this. Cool. Sorry about that stream. So yeah, after the bus support and the no connections, there's label support. So you can add a label onto your net. And again, your net is just the connection point between your two components. You can also have flags. So to make your schematic a bit easier, and if you have, instead of having a connection between a component on the very top left-hand side and a very bottom right-hand side, sorry, you can just add a global label. And KiCad's going to recognize that this label matches with this label, and there's going to be a net or a wired connection between the two labels. And then moving on down just a little lower, there's support for adding text and then adding images as well. So starting with actually building this thing, we're going to be including a bunch of different components. So KiCad comes in with a bunch of standard libraries that have just all your standard components that you would use, like resistors, capacitors, inductors. But they also have a whole support for other components like LEDs, different integrated circuits, and stuff like that. It's actually pretty well-rounded, but it doesn't include everything. So that's why they also include the support for designing your own schematic or designing your own symbols and your own footprints as well. So to start it off, we're going to need LEDs, resistors, and a connector. So if you just type in LED, the default one is good enough for us. So you can just double click that and paste this in by clicking on it. And then to add in the next component, you can just click again, type in LED, and add it in. Or what you can do is just select a component, Control-C and Control-V it, and to copy and paste. Now, the rotation of these components, I don't really like right now. So what you can do is just click on a component and hit R to rotate the component itself. So I kind of like it facing down and right there. So I'll change all three of them like this. So after that, we need our resistors. Which is just, where is it? It'll just be R. And then again, we can just select and copy and paste it in like so. So we have our LEDs, our resistors, and so at the bottom of the resistor, it'll just be a ground connection, which is specified by a GND. Oops. To move components, you can just select them and then click and drag them to wherever you want. And I'll just pause there for now, just how everyone's doing. Does everyone have at least their components on their schematic? So that's our 3 LEDs. And then we'll also need a connector as well. So connector, connectors. So there's actually 2 different types of connectors. There's connector. Oh, sorry, yeah. You have like the grid. It's there for me by default. But if it's quite faint for me on my screen, but I'm not quite sure how to change that. Oh, if you go to view and then show grid. If if you go into grid properties, oh, it just specifies the size. Yeah, sorry, I'm not too sure. Sorry, so we'll add in our connector. I like using the generic connector because you can always assign your footprint later on, and it's easier to make that change with a generic connector. So we have 3 LEDs, and then we'll also have a ground connection. So I'll include a 1x4 connector. Cool. I'll zoom in. And then these are all the components, but then we can also include our mounting holes as well. So this is the generic connector. And then once we've done our connections, we can assign it a male or female in the footprint step. No, I can't. Cool. And so now we have all our components on our schematic. We can go ahead and form all the connections. And so that's as simple as selecting the wire tool on the right-hand side, and then going over to the connection point and just clicking on one connection and then the next. For the connector, what I'd like to do is use the global labels. And so what we can do is call this one LED red. Put that in, create another label called LED yellow, put that in, make another one LED green, and put that in. Rotate them so they fit. And bring them closer to the connector. And then attach a wire to the flag and the connector. And now, instead of having a wire specifically from the connector to each one of the LEDs, we can just copy in each one of the the global flags, and attach it to our LEDs to make it just a bit prettier. And connecting each one as we go. Cool. How is everyone looking? Everyone able to lay out or connect all their components, add in a connector, use the global flags. And one of the reasons why I like using the global flags is what you can also do is create little sections of your schematic. with this Daft blind tool. And what you can do is just use that, select a location around your components, and just box it out just a little bit and finish the line. So that way, as KiCad, you are limited to just your to just this one screen. Having just a bunch of wired connections and just a bunch of different components kind of scattered around, it can get really, really, really busy really quick. And so a good practice is just to box together like components and then provide a label onto that, just so if anyone is working on it in the future, they can come in and know exactly what this section is for. So this section will be only for the LEDs, and everything required just for the LEDs. We'll have a connector section and then a mounting hole section. What I also like to do is, if we have like a MCU, have an MCU section, and then use global flags again if there's any external connections or additional connectors that they have to branch off to. So for example, you could have an MCU, have a global flag of your MESO, MOSI, and your clock lines. And then where you want to use those SPI connections of the MESO, MOSI, and clock lines is just another connector in the same kind of configuration. So I'll do the same thing with the connector. And the mounting holes. Cool. So just finishing up the last connector, I see I forgot to include a ground. And we'll just include that right there. And then you can also move the component, but then also the associated tag itself separately by just clicking on the name itself. Mounting hole, ground. So on each one of the components, when you place them in, you'll see that by default, it has these question marks. So what these are they're the reference values for each one of the components. So each component has to have a unique reference value, so KiCad can keep track of it. So you can either do it one of two ways. You can manually enter each one and label this one D1, D2, D3, J1 for your connector. Or you can go at the very top and where it says fill in schematic symbol reference designators. You can see the icon is a little R question mark with an arrow that points to an R42. This is the little menu that it shows. So you can choose the scope of what you're going to update. So we want the entire schematic, the sort symbols by X position or Y position. So for our case, we want it to go increasing from left to right, so across X. And then there's just some other options and numbering. So all you have to do is hit annotate and then close. So now everything is designated a unique value. So they did that with the diodes, the resistors, the connector, as well as the mounting holes. So this looks pretty great so far. It looks very clean, very readable. And we have all our schematic already finished. Great. Cool. Does anyone have any questions, comments, concerns? Yeah. Sure. So at the very top, there's this symbol with the R question mark to R42. So if you just click that, do you have this? Okay. And then you can just change some parameters. I usually just choose all the default ones, and then you just hit annotate. Perfect. Okay. Yeah. If you don't want to go that automatic route, or if there's something specific you want to change about a component, you can double click the component and then have all the parameters associated with it come up. So each component has a reference, a value, and a footprint. So the reference is just the name of the component. The value is going to be like the numerical value itself. So in our case, we have a resistor, so it'd be the like 100 ohms you would put in for the value. And then of course the footprint, so the associated the associated footprint with the component. So in our case, standard resistor value for just an LED that we saw earlier is 330 ohms. So we can just put that in and hit OK. And so now you see it'll automatically update it on your screen. For the LEDs, we can do the same, but instead of a value of a LED, we can just specify this as red, which works just fine. So I'll do the same thing, oops, across the board. And mounting hole connector, that's all fine. Cool. So we basically have our schematic finished. I know we haven't done our footprints yet, but I'm just going to show you the how to then convert your schematic into your PCB. So at the very top, you should have a little icon that shows a PCB. This is Open PCB in Board Editor. So then this is going to take us to the PCB new program, in which we're actually going to be performing the layout and the routing of all our components. The main tool that we're going to use here right now is at the very top. It says Update PCB with changes made to the schematic. So if you click that, we have a bunch of errors, which is as expected, because we have not assigned any footprint. So before you actually go ahead and go into your PCB, you are forced to update all your footprints. So thank you, KiCad, for getting mad at us. So we'll go back to our schematic, click on our components, and then go to where it says footprint and click on the little library icon. And so as we saw with the placement of the components onto the schematic, there's a whole list to choose from. There's also a whole list of footprints that we can use to associate them with the component. Yes. Oh, sure. So if you click on footprint in the little text box, there's this little library. If you just, so just from here, if you just double click on the symbol, and then click on the little library textbook. So we're looking for an LED. And so this is why I mentioned surface mount and through-hole technology prior to. So THT stands for through-hole technology, and then SMP stands for surface mount device. So we're just going to keep it simple. All the LEDs we have in the room right now are just through-hole. So we'll look for through-hole. And then you're met with a whole list of different footprints you can assign to your component. I know it can be a little overwhelming at first, thinking which LED is the right one or which footprint is the right one. Because KiCad allows you to be so flexible, there is so many choices to choose from that it can be a little daunting. But right now, for our case, the standard LED that you would just pick up off the shelf is just the 3mm one. So you can double click that, and then it gets assigned to the component itself. And so we'll do that for each one. Go in and assign each component its footprint. What's the THT? That's for through-hole technology. Yeah, it's just to separate through-hole from surface mount. Yeah. Yeah. Which LED footprint did you use? Oh, sorry. I used the 3mm one. I'll go back to that. Yeah, this one right here. Okay, and so then we'll do the same thing with our resistor. So we'll search resistor, select through hole, and if you thought LEDs were annoying, there are a lot of resistor footprints to choose from. They're all specified by a length, a diameter, and a pitch. The length is the actual actual length of the component of the resistor itself. The resistor kind of looks like this. So I believe this is the length. This is the pitch, I believe it they use. No, sorry, diameter. And then the pitch, which is specified by the P, is the length that the leads can come out. So this is your pitch, and that's your diameter. So what we're looking for a standard quarter watt LED or resistor is going to be 6.3 length, a diameter of about 2.5, and then yeah, a pitch of about 7.62, and it'll be horizontal because we're going to lay these flat. What you could do is have the LED, or sorry, the resistor actually stand up on top and go like that. That is one way to mount resistors. You really only need to do that for power resistors that generate a lot of heat. So we're not going to do that today, but just so you guys know, this is your vertical, and then this is your horizontal. And just that's the reason why they have both vertical and horizontal configurations here. Anyways, length of 6.3, diameter of 2.5, and a pitch of 7.62 is what we're going to go with. So we'll do that again for each one. Oops. Cool. So we've done LEDs, we've done resistors. Now we have to do the footprint of our connector. And then this is to answer your question. Is this male or female? This is really up to you to decide. What we're going to do and what the footprint's going to look like is just 4 holes in the PCB. So you can mount a female connector or a male connector on it. It's really up to you. The example in the slides, if it'll show, does use a male connector with a 90-degree offset. I kind of like this because it's really easy to interface with other designs. So I'm going to use this same one, but you guys can use any other kind of connector you want. So to find that, it'll be connector, and it'll be either a pin header or a pin socket. A pin header is a male connection. A pin socket is a female connection. And you'll also see there's a measurement beside each one. So 1 millimeter, 1.27 to 2.54. What these indicate is the pitch of your connector. And what that is, it's the separation and the distance between the different pins. So for example, you have a connector. I'll draw a male connector. And so the pitch is the distance between the adjacent pins. Standard sizing is a 2.54 millimeter pitch, and that's just for the PC104 connector, the PMOD connector, the Arduinos that we use, the Raspberry Pis that we use, all the headers on them, they're all a 2.54 millimeter pitch. It's just a standard size used. So I'm going to use pin header, which is male, and then 2.54 pitch. And then we want a 1.5 or a 1 row 4 column vertical. So the default view that they give is just the associated footprint. But KiCad's actually kind of fun, and you can see the associated component with that. So to get there, you click on the component you want, and then there's this little like through hole component icon at the top. You click that, and then you can see one of the connector associated with that footprint. So that's a 1x4 header connection with a 2.54 pitch. So what we can do then, go on to the horizontal one and see, okay, this is roughly the one that we want for the 90-degree turn. So I'll select that one and hit OK. Cool. Anybody have any questions about connectors? Sweet. So we've done LEDs, we've done resistors, we've done connector. Mounting holes are our next step. So again, search mounting holes. And again, there is many to choose from. Standard sizing for mounting holes are just to associate it with the mounting hardware that you have. In industry, standard sizings are through metric sizing, so either M2 or M3 screws. For a little debug board, we don't need anything super mechanical or super strong, so we can opt for just an M2 mounting hole. And so that'll be all designated by the first section. And so again, even if you just choose M2, there's a bunch of different supports for those as well, all associated with the outer ring and the outer pad that can be applied onto it. So if we take a look at this, the M2 specifies the diameter of the hole, but then all the different configurations include the different sizes of the what's called an annular ring around the hole itself. And so we can see the difference between this. So this is just your standard standard hole with the M2 size. But then if we want a pad on it for a little bit of protection, we can use this mounting hole. I think these look a little prettier, so I'm going to use that for myself. And then just go ahead and assign that to each one of your mounting holes. Cool. Sweet. So we've done the schematic steps. Yes.
This mounting value that you put in there?
The footprint. It's the 2.2 millimeter M2 with. Cool. So yeah, just to recap, we've done the schematic steps, putting out all our components, connecting them all. Then we just finished the footprint step. So we assigned all the footprints to each one of the components. And so now we are able to go into the layout and routing of our PCB. So again, to get there, you can go into Open PCB in Board Editor. And then once this is open, you can use the tool that says Update PCB with changes made to schematic. So now this is going to take in all the footprints that we assigned. As you can see, it adds all the mounting holes, the connector, all the diodes, and all the resistors, and all the associated footprints. So then you can just hit Update PCB, and we get this mess. So now it's our job to lay this out properly in such a way that it's actually usable. So zooming in a bit more, we can see all our components are placed. And you'll also see all these white lines. These are called a spider's web. And they are showing you all the different nets and all the different connections that need to be made. So you can see that this resistor gets associated. Oh God, who knows? Okay, it looks like this resistor gets associated with this LED, this resistor with this LED, this resistor with this LED, then all your directions are connected. It's just the way KiCad supports you in making sure your signals don't get crossed. So going into the actual layout, you can select a component and just drag it anywhere you want. And same trick that we use to rotate, you can just select a component and hit R to rotate it around into your proper configuration. One tip that I like to do for PCB layout is kind of start with my connector on one end and work my way from left to right. And just kind of envisioning myself actually handling the PCB and like plugging it in onto the far side of the screen and kind of what needs to come after that. So just putting some thought into it. So we're going to have a connector over here. From our connector, we're going to go into our LED, our resistors. And then from our resistors, we're going to go into our LEDs. And then our mounting poles are going to be in our four corners. So what I usually do first is just do a rough layout. And just kind of move everything in a general location of where I want them to be. Okay, so kind of like I said, start with connector, go into our resistor, go into our LED, and then have a mounting poles on the corner. So cool. KiCad actually offers another cool trick, just as we saw, or how we saw the what the connectors looked like in an actual like 3D rendering. We can also see what our PCB looks like as well. So if you go into view and then 3D viewer, select that, it pulls up a really cool, fun, awesome representation of what our PCB actually looks like. It doesn't do the best job because we haven't done any bordering or edge cuts of the PCB. KiCad just kind of filled in its best approximation. But you can see we're on the right track. Our resistors look good. Our LEDs look good. I like the connector, and then the mounting holes all look fine. So I'm pretty happy with this so far. So once I have them in their general location, I then like to do the routing. I don't want to bring my components too close to one another because if I do that, I might not leave enough space for my routing and eventually just have to move things again. So I kind of like this. I might straighten this up just a little bit more. I might move some of these silk screen labels to be something a bit more visible. But after I do that, I'll go right into the routing. Okay. I also just want to point out some other features in this PCB editor. So as we talked before, your PCB is made out of all these different layers. And so each one of the layers is actually shown on this side here, and each one is color coordinated. So we haven't done any of the actual routing itself yet, but you have your two copper layers. As you mentioned, this is going to be a 2-layer board. So you have a front copper and a back copper. After that, you have your silk screen. So anything in yellow, like this D1, these lines on the LED, this little box around the resistor, and the R1, those are actually going to be silk screen. And I should have pointed that out here. And so that's what can actually be seen on the actual board in that white text. The yeah. So, and then each component also has this purple box associated with it. This purple box is called your keep out area. And so this just specifies just the maximum footprint your component needs to actually sit on the board. And so just as a rule of thumb, of course, you never want to have your keep out boxes overlapping. Makes sense. Okay. Cool. I'm pretty happy with the layout of the connector, resistor, and LED. So I'm actually going to start laying out a trace. You can do that by selecting this trace tool right on the right-hand side. KiCad comes with predefined trace widths, but I like to set my own. The way you can do that is on the top left-hand corner, select use net class width and hit edit predefined sizes. So but here you can specify the size of your tracks or your traces, the size of your vias, how big the hole is, as well as the annular ring or like the pad associated with that via. And then as well, you have settings for your differential pairs. Differential pairs are used for like USB signals, and there's quite a bit of work that goes involved with differential pairs, as they need to be the exact same width, exact same spacing, and the exact same length as well. But for now, we're just going to create a new track with a new width. And I like to use just 1 mil tracks. So it's 0.254 millimeters. And hit OK. So then just make sure you select that track and it says your track size and not the used net class width. And then after we've selected that, we can select our track tool. And then it's just a matter of selecting a location on the board. And KiCad does a good job of using that spider net and just highlighting where your two nets need to be connected. So I'm just going to come out, go like that. And then I can do the same thing down, across, up. Up. So now I've connected the connector to the LED, and now from the other side of the LED to the resistor. And then, okay, now we have a problem. So have a ground connection on each one of the resistors. But to go from this ground to the ground on the connector, we have two traces in the way. Because we're using a 2-layer board, what we can do is select the bottom copper layer. And so now every trace is now going to go on the very bottom of the board. And they're going to be colored in blue, as opposed to these traces which are on top of the board and are labeled red. And so we can just go directly I don't like that. And connect all the grounds together. Now, if we wanted to, we could have also used a via and come out on the top layer from this connection, go down into the PCB with the via to the bottom layer, scoot it up to the PCB, come back up with the via and go into the ground. However, since this is just a through hole, we have access to it from top and bottom. So that's a little unnecessary. Cool. So now I'm just going to move my mounting holes a little bit closer in to minimize the size. And make sure they're all cool. And then we can take a view of what our PCB looks like now. So sweet. So KiCad actually does a good job of rendering out the connections. So we can see on the top layer, we have that trace. And then if we turn the PCB around, we can see the traces on the bottom layer. So we can just verify all our work. And I'm pretty happy with it. I don't really like the silk screen for the mounting hole designators, so I'll remove that. But the red, yellow, green silk screen, J1 silk screen, that's what's all good to me. So let's just change that and then go into our edge cuts. So to change properties of the text you see, so each one of the texts gets assigned to a layer. And so if you just want to move that to a layer that doesn't actually show up on the board, you can go into either the fabrication layer or user drawings. And so now you can see that they got grayed out and they will no longer show up on the silk screen. Cool. Now we're going to the edge cuts of the board. So we're going to specify the outer border of the PCB. So again, we can choose from the right-hand side the layer called, where is it? Edge cuts. So select that. And then we can draw with the tools on the right-hand side, just a surrounding box around all our components. Just like so. And then again, take a look at our PCB. So it's looking pretty good so far. For the connector, we could extend the edge cut just a little bit further. So there's a bit more support on the bottom. So we can do that by just dragging that. So the two locations that I'm allowed to put my edge cuts extends past the connector or doesn't provide enough space, or it's too far in or too far out. So what you can do is change your grid size to be a step below, and now you have a bit more flexibility and finer resolution on where you can put your components. Yeah.
Do the edge cut again.
Sure. So if you select the edge cut layer on the right-hand side, and then select the draw tool with the line, and then just select the corner of your PCB, and then just drag it across to where you see it. And then again, we can just connect up. So I like to have my mounting holes right in the corner, so I'm going to move those just a bit. And I'm not the biggest fan of having the squared off corners. So what you can do is add in a curved line with the curve draw tool. Never know how to use these. And add in your curve. Awesome. And then we can take a look at our nice, beautiful curves on each one of the mounting holes and see that our connector has pretty good support on the bottom. How's everybody looking? Yeah.
How did you remove the silk screen tags?
Sure. So what you can do is select the text and then just change the layer in which it appears. By default, it's on the silk screen layer, so you'll be able to see it. If you move it to the fabrication layer, it will show up on the final product. Cool. Yeah.
How did you select just the corners to get the least from the edge?
Sure. What I did was selected the line, and then on the edge, I just brought it back. Yeah. Does that work for you? Yeah. Are you not able to drag it back? What you might have to do then is just add in your curve and then just delete the old line and draw a new line connecting the two curves. Where's everybody at with their little traffic light? But so that's basically all I wanted to cover today. We did a lot. So we did schematics, we did footprints, we did layout, we did routing, and we made a final product of a little traffic light. We looked at different silk screen techniques and different edge cuts that we can use as well. There's just one more feature of KiCad that I wouldn't mind including, not in this design, but just mentioning as well, something called pores. And so instead of using just traces, which are basically just a wire, you can have a pore, which is like a large copper pad that you can use and connect to with vias. And so what that looks like is, I believe it's this one. So it's at a filled zone. And what you can do is just draw, whoops, make sure you select the actual layer. So you can assign it a net and then draw in a filled area, which is now just a large space. And then you should be able to fill in that board zone. Do I remember how to do this? There we go. So yeah, you have to have a connection to it. But now this red square is actual core of copper that you can use. And what you would want to do this for is typically with a 4-layer board, you'll have a signal layer on top. So kind of what we did, we routed all our signals. The next layer would be a ground layer. So the entire board would be solid ground. And so this whole square would cover the entire area. And so the purpose of that is instead of having a ground connection between multiple components, all you would have to do is from your component, go out, use a via, and then connect to this, to the ground plane that's accessible everywhere. So now the amount of traces that you have are a lot less. And as well, your impedance between your two grounds is minimized. It also helps with like RF interference because you have this solid ground plane that actually blocks out a lot of EMI or electromagnetic interference between the components. Same thing. So on the top layer is usually a signal layer. Next layer would be a ground layer. The one after that, your third layer, is typically your power layer. So either 3v3 or 5v0. And so again, if you are powering a chip or a device, you don't have to, from your connector, go across all your different chips. You can just, from your component, connect to a via and just drill straight down into that power plane. This way, there's a smaller path between the power source as well and the chip, which reduces capacitance and inductance and causes higher stability in your power delivery. Because usually what you do is with an IC or like a sensitive like transceiver or something, you would have your what's called decoupling capacitors. And what those do is they'll smooth the input power that's received from your power layer, because there can be a lot of noise from your power layer delivering all the power to all the different components. So you'll have your power layer, your decoupling capacitor, and then your actual component. And then the space is minimized because all you're doing is just going from one layer up to the next and then directly into that decoupling capacitor and that component. And then your final layer, your fourth layer, would just be another signal layer. So you are able to do the trick that we did and jump up and down between the two. For a small design like this, it would be way overkill and very unnecessary. But for the designs that we're doing with comms, OBC, ADCS, and EPS, using that 4-layer design and separating out signals, ground, and power are going to make routing a whole lot easier and actually like improve the integrity of the electronics. But I just wanted to mention that. I know we didn't really use it, but know that it's there. Cool. So just to finish up. So I know I moved pretty quick, but that's fine. We can continue with questions after this. But I just want to mention some just general tips. I mentioned vias and trace widths, especially when it comes to differential signals like USB. Determining those sizes, you have to look at the limitations of your fabrication house, which is the company that actually makes the PCB. So this can be either Osh Park, JCL PCB, or PCBWay. They have limitations on what they can provide. And they'll be straight up with you and tell you what these limitations are. So as we go through our projects, that's something we're going to have to consider. For trace widths, you get there's an associated cost with the number of different traces and the number of different holes that you use. So I like to just do a small, medium, and large trace, all incrementing by that 0.254 millimeter. So usually I'll have, this is 0.254 millimeter trace for my signal lines. I'll double that if I'm bringing in multiple signals or multiple grounds together, just so it has a lower impedance. And then I might have like 4 times that if I have this massive power input, that's going to be powering the whole board, for example. As well, so we've talked about, or I've alluded to differential pairs. KiCad does have a feature that helps with differential pairs. You'll recognize that a signal needs a differential pair. Usually by at the end of the signal, there's a plus and minus sign, or a P and an N. In KiCad, if we're doing our own schematic and our own schematic, what we would do is label our net with our underscore N and underscore P, and KiCad will recognize that right away as a differential pair. And what you can then do in your PCB is go into, where is it? Here, yeah. Add in your width, your gap between the two pairs, and the gap required for your vias if you're using them. And then KiCad will, as soon as it sees a net with a P and an N, if you start routing, it'll actually route both of the pairs together, or the pair together to your P and your N. As well, when you have a differential pair, there's something called the skew, which is the difference between the trace lengths. Because you're routing, you have a component here, and let's say a connector here. If you go here, 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 since this trace is going to be longer than this one, but you need them to be the same length, because if they're not, they're going to be different resistances. And if they're different resistances, your signals actually may approach the connector or approach the device at different times. So what you can do is change the skew or change the length so that both traces are the exact same length, and it'll usually do something like this. And so now you have the lengths matched, and now your signal integrity is intact, and your differential signal will be arriving at the exact same time. I don't think we do too much of the differential pairs. Maybe if we're just having a USB signal, but I just wanted everyone to be aware of that as well. Cool. And then last but not least, because this was just kind of a quick first step, I wanted just to point out some additional resources as we work towards our boards. There's a YouTube channel called Phil's Lab. He is a hardware designer somewhere, I believe, in the UK, and he is absolutely phenomenal. He does lectures, he does full-on breakdowns of beginning to end KiCad projects, going over everything that we did and more. He does a lot of work with STM32s, building breakup boards, buck and boost converters, impedance amplifiers, just you name it. He has a whole channel dedicated on PCB manufacturing. and electronics design. So I highly recommend that. Of course, the KiCad documentation, there's a lot of just tips and tricks that are in there that I encourage people to read. As I mentioned, with the differential signals, your impedance of the line, which is like the resistance of the line, has to be equal. There's tools for that. And so JCL PCB, which is a PCB manufacturer, they provide a calculator for that, which is very helpful. And as well, our final product is not what we don't just provide a KiCad file to the PCB manufacturer. We provide Gerber files. KiCad does have a feature to convert the KiCad file to a Gerber file. And that's what you would then provide. Each one of the fabrication houses, so JCL, PCB, PCBWay, Osh Park, they all kind of want them a little differently. So we do have to be careful of that. But I just provided a link for the JCL PCB one, because it specifically asks or it shows you how to convert them from KiCad version 6 into the format that they want. And then we didn't do this on our own, but I alluded to in the beginning, you can add in fun logos and graphics. So if you have like the QSET logo, or if you have your own little personal logo that you want to throw in, you can do that and have it show up on the silk screen of your piece. So lots more to explore, and I highly encourage people to do so as they continue with their projects. But yeah, that's it.